All right, I'm going to go down a couple of problems here on practice 18 for kinetics part 2. And I'm not actually going to work them, but I am going to talk about how to set them up. And if you want to see one worked out, please ask on the discussion board. This page is sort of focusing on integrated rate laws and have those equations handy. The lecture videos talk about those equations. Your textbook lists them all out. Have those equations handy. You might want to have them in a couple different formats, solving for different things. But the integrated rate laws are used when you know 3 of the 4 variables for a reaction and you know what order it is. And so basically what's going to happen as we see these problems is they're going to tell us you've got a first order process, you've got a second order reaction, you've got a third order reaction, a 0th order reaction. So they're going to give you what the order is, and then you're going to go from there to work the problem. It's going to give you information about concentrations and time, etc. And from there, you're going to work the problem. And so that's always your starting place. All right, so here we have a question from practice 18. For a certain first order process, they're telling you it's first order. At 250 degrees Celsius, the temperature doesn't matter. It doesn't show up in any of the integrated rate law expressions, but recall from the module, your temperature has to be constant in order for your rate constant to be constant. So that's just telling you you've got a constant rate constant. You begin with a 250 gram sample, and there is 1.5 grams remaining after 109 seconds. What is the rate constant for this reaction? I'm told that it's first order. I know what the first order integrated rate expression looks like. There are a couple of different ways to express it. One of my favorite ways to express it is that the log of the concentration at time t over the log of the concentration initially, that's all inside the log, is equal to negative kt. There are other ways to do it. I can do a sub 0 over a sub t, and that equals positive kt. I can write it like the equation for a straight line. For example, I can write it as the log of the concentration at time t equals negative kt plus the natural log of the initial concentration. These two equations are identical. They're just, you use algebra to rearrange them. Put them both on your equation sheet that you get to have during your quiz and your test. Quiz is completely open book, but I'd still organize my notes for it. You'll notice in this problem, we have an initial, it's not a concentration, but it's an amount. And for first order, it doesn't matter. It's 2.50 grams. The concentration, or the amount, for first order, it can either be the concentration or the amount, at time t is 1.50 grams. And the time is 109 seconds. And the rate constant is what you're looking for. Take this equation, plug it in, your values, solve for k. The only thing you really have to be careful about on these as far as units, you don't have to keep your units along as you do it, but you do have to make sure that the units on your time matches the units that are expressed in your rate constant. If they're not, change the units on your time. Change your time to match the units in the rate constant. So plug and chug. Come down to question 2. I am told it is a first order reaction. I know what equation I'm dealing with. I'm given the k value. I'm not going to rewrite it out. K is that value. How long does it take? T is what I'm looking for. For a 10 gram sample, there's my initial amount, to be reduced to 8.35 grams. There's my amount at time t. Plug into that equation. Hydrogen peroxide decays into water and oxygen in a first order process. K equals this. The initial concentration is this. The time equals 2 hours. What is the concentration at time t? Here you do have to watch your time units. Time is 2 hours, And you'll see that your rate constant is given in seconds, so convert that to seconds. You can use a Google converter if you want to. Ask Google how many seconds are in 2 hours, or you can do it by hand. Plug and chug. Now in this one, we have a second order reaction. My equation is different for a second order reaction. What's the equation for a second order? Again, there are various equations for second order, various ways to express it. They're all the same equation. One of my favorites is that the 1 over concentration initial, and I'm getting this right out of the textbook, equals KT plus 1 over the concentration. Oops, I got them backwards. This is time, T, and that is initial. I often write this, I think in the lecture videos, I probably put it like that. Again, these two are exactly the same equation. They're just algebra. So what have I got? I've got an beginning with that concentration. There's my initial concentration. After 243 seconds, there's my time. Let me grab another color. There's my concentration after the 243 seconds. What is the rate constant? K equals question mark. If I look down here at the units, my rate constant does have units of seconds. The time is seconds. All is good with the world. Plug into that equation. Watch your algebra. Second order. Again, same equation. You start with either one. It doesn't matter. Look for your values. The rate constant is that. Notice it's in minutes, so I get a rate constant. There's my initial concentration. The time is 30 minutes. There's my T, and you'll notice it's in minutes. My K is in minutes. All is good with the world. And what is the concentration after that 30 minutes? That's what I'm looking for. Watch your algebra. You can use algebra solvers on this if you want to, but it's almost as quick to do it by hand.